Hi, and welcome to my presentation on parameter conditional reachable sets for online safety assurances. My name is Javier Borges, and I'm a PhD student at USC in the Safe and Intelligent Autonomy Lab under the supervision of Somil Bansal. Let's imagine that our task is to navigate a drone safely. Some of the challenges are uncertainty in the environment, because obstacles and targets might be moving around, or different levels of disturbances as the intensity of the wind blowing changes, or even diminished control authority as the battery depletes. If we want to remain safe, we must adapt quickly to these situations. For simplicity, only consider the uncertainty on the speed of the wind blowing. In this scenario, we want to reach the green target, and for no wind speed, we can imagine that the states that can reach it safely are the ones colored, and that the drone can take the short route between the two obstacles. Now, if we have strong winds, passing through such a narrow gap might be unsafe, and the set will look more like this, indicating that we should take the longer route. The problem is that wind speed might change as we are executing a trajectory plan. So we would like to be able to adapt online and change the route in that situation, as shown in the dotted trajectory. One of the tools available to construct this set of states that can reach the target set safely is Hamilton-Jacobi reachability and the notion of backward reachable to, or BRT for short, which considers all states that for some time horizon will be able to reach a target set by having the optimal control applied at all times. The formulation requires the dynamics of the system, here presented as a function f with state x, control u, and disturbance d, and an implicit representation of the goal states, usually a sign distance function. With that information, and by solving the Hamilton-Jacobi PDE, we get an expression for the BRT and the optimal controller. This Hamilton-Jacobi-Isaacs PDE is usually numerical solved over a grid that contains the area of interest on the space of states. The main challenge is that any variable for which we want to adapt online behaves like an extra state dimension for numerical calculation purposes. And because the grid scales exponentially with state, this becomes unpractical, except for the simplest systems. To work around this, we propose to use recent advances in DNN approaches to approximate solutions for this Hamilton-Jacobi-Isaacs partial derivative equation, where we take system, state, and environmental parameters as inputs, and we get the value of the PDE solution at that point, allowing us to construct the BRT and optimal controller. Running simulations using the proposed method on our drone examples, we get a BRT that changes shape for different wind conditions and selects the corresponding optimal safe control to reach the target in each case accordingly. Now, only visualizing trajectories, we see that if the wind condition is maintained during flight, it takes one of the trajectories previously shown. But if wind condition changes mid-flight, it is able to adapt and take the new safe optimal trajectory as needed. In a new example, we consider the upright landing of a rocket on an offshore landing pad that moves within some range as it floats in the ocean. As for simulation results, on top we have a 3D plot where trajectory, target, and BRT are shown and how they evolve over time, while in the bottom we have the 2D slice for the current time step. Here we can see that a controller based on our approach successfully tracks the landing pad. But more importantly, by having a notion of the BRT at all times, the system knows if it's going to be able to land safely in the future by checking if the current state is inside of the safe set. If the landing pad were to move too fast and the rocket finds itself outside the BRT, the maneuver can be aborted before it crashes into the sea while making a futile effort to land. To conclude, we remark that we presented a method to update safety assurances online through parameter conditional reachable sets. Our method relies on the recent advances in high-dimensional reachability to quickly update reachable sets online, and that the use of DNN-based methods allows us to work around the issue of high dimensionality of the system. And on the drawback side, this particular work presents no formal guarantees as the solution for the PDE is being approximated. But a second work submitted by our group at this conference is addressing that limitation. Thanks for your attention. For more information, you can go to this work website by following the QR code presented, where you'll find more examples and a link to the paper and the source code.